Good morning. I'm Sonja Dieterich, currently a professor at the University of California, Davis. You can also find me on Twitter. And today I'm going to present on guidance for computational and systematic error prevention methods. This is my conflict of interest statement. Our learning objectives for this lecture is to understand the background and motivation for implementing computational and systematic error prevention methods. Discuss which computational methods are currently in use clinically and what are their advantages and shortcomings. Also, what systematic methods are in use and what are their advantages and shortcomings. When I think about IMRT, QA, and safety, I always think about this idea of the quality trap that Peter Dunscombe often used to talk about. He was making an assumption that we have a Gaussian distribution of the deviation from the ideal treatment, with the majority of our patients receiving benefits. There's, however, also a very small percentage of patients that come to obvious harm with high severity events, like we have seen in the New York Times articles. These events are luckily very rare. But between this area of benefit and this area of harm is the so-called quality trap, where there are no obvious injuries, but the probability of the desired outcome is compromised because we are deviating from the ideal IMRT delivery. To reduce the standard deviation of the normal distribution I just showed you, we need to take our resources, that is machine time, the equipment we have in our department, and the number of physicists, and optimize these parameters for maximum safety. It's a Pareto front, hopefully, where there is a set of optimal solutions. Because these three input parameters are different between different clinics, the optimal solution might actually differ. The optimal solution is also a function of the year you're looking at this, because equipment, software, and safety science are changing over time. The other thing I'm also thinking about is that we as medical physicists often view safety as an optimization problem for high numbers of patients, high N. But we shouldn't forget that for patients that fall into the quality trap or even come to harm, it's an N of one. It's their one life, and for their family, it's their one mom and their one uncle, sister, the one person that's important in their life. And, this whole workshop is actually on finding where that balance is between trying to optimize safety and always thinking about that even if there's a very few number of people up here in the quality trap and harm, that it's a very, very important person that affects this. So I will start where Dr. Mifton left off. He talked a lot about QA measurements, and very soon after QA measurements were introduced in the clinic, medical physicists started to do log file QA. And the reason why log file QA came on into the clinic was that medical physicists realized that this delivery QA measurement we do before treatment is one instance in time before the start of a several-week-long treatment. So based on what we used to do for 3D, we were thinking, well, can we do in vivo QA for IMRT? Diodes didn't quite work well for IMRT, obviously. And at the time IMRT was implemented in the clinic, EPIDs were new, challenging to calibrate, and in-house software was the only option to get fluence maps out of them. But what we also knew is that engineers use machine logs for error root cause analysis. So medical physicists started to look into, okay, what information can we find in machine logs and what can we do with that information? And also we needed to figure out what's our plan B if our only IMRT measurement device breaks once we moved away from film and film processors. So what medical physicists learned is that based on the log files, you had all the machine parameters available that could be used to forward project a fluence map and compare that fluence map to the treatment planning system. And that led to a little avalanche of publications in that topic. As for what fluence map would pass or fail log file QA, the same general guidance was applied as is outlined in the measurement QA for TG218. A lot of the papers started studying the magnitude and frequency of deviations from the planned treatment during fraction n during the course of the treatment. So here's an example of what that would look like from one of the papers I like from Dr. Rangaraj. So they had a 7-field IMRT-QA and they had certain pass and fail parameters here. And here on the right side, you can see for each of the fields, they had a fluence map that was calculated from the Dynalog. They had varying equipment, a fluence map from the treatment planning system. I believe that was Pinnacle. And the fluence map difference, you can apply a gamma analysis to that fluence map according to the paper from Dr. Lowe. The earliest publication I found on the topic was actually co-authored by Jean Moran. So Dr. Rangaraj did one of the earlier large-scale studies to determine the error rate. And what they found that out of the 912 log files they studied across a number of sites, they actually had a very small error rate. 1.5% of log files exceeded their tolerance, and none of them were catastrophic. And they also did an analysis where these deviations originated from. And a lot of them were actually data transfer problems. So there are some shortcomings of log file DQA. The log file write process can have catastrophic errors. For example, files are just not written at all or are corrupted. The log file process can also be interrupted. For example, in my equipment I have in my clinic, the log file is stopped after 1000 MU and then restarted again. That comes from an old 3D MU limit and causes problems in VMAT SBRT deliveries which have more than 1000 MU per treatment path. And another issue is if DIBH beam holds exceed 20 seconds. And what I've recently realized is that the sensors in the LINAC could also potentially cause deviations, because if they drift and they're not into the catastrophic failure, but in that quality trap we talked about, minor deviations, these sensors could actually give us slightly incorrect information that is written to the log file. And I put this picture in here because I have that situation with a temperature sensor in my kitchen oven. It's not causing the oven to fail, but the products are clearly suboptimal because the sensor is not reading the correct item. And that happens in Linux presumably as well. So from what we've seen so far, we have two goals of the DQA measurement. One is verifying accurate and precise machine performance. The machine is meeting the standards that is outlined by standards and regulatory organizations. And the second part is that we're trying to verify the data transfer chain. As we've seen in the New York Times articles, that was one of the major problems that led to catastrophic errors. One of the recent task groups published by AAPM is Task Group 201 on quality management of external beam data transfer. The charges of this task group is to recommend processes that are robust in the presence of errors in electronic data transfers, and to recommend test procedures that prevent mistreatments due to corruption or misinterpretation of radiation therapy treatment data. How that looks like specifically may strongly depend on your department's IT infrastructure. So on the left side, you see a department in a multi-vendor environment where the databases are distributed across delivery systems, the treatment management system, treatment planning system, that all come from different vendors. Or you might have a single vendor environment where there is a main database from which information gets transferred out in a star-shaped fashion to the different components of the treatment delivery. So what TG201 recommends is that the very first thing you do is create a data transfer matrix with the source of data up here in the columns and the destination up here. And that gives you also the direction of data transfer. And then in the matrix itself, you can list the types of files that get transferred between the various components. For example, here the treatment planning system to the treatment management system that receives the plan and images. And then you have for each position in the matrix, for example, the TPS to the TMS, you have a series of potential issues that could come up and methods how to do QA to check that these data transfers are actually handled correctly when you install the system. Now, QA, daily, monthly, annual, is not quite enough. You also need to have quality control that ensures that an individual patient's treatment meets the intent of the physician's prescription. So for that quality control, you have two distinct elements: integrity of the data between source and destination subsystems, and logical consistency of the data set after the transfer. And same as before, for each of the elements in that data matrix, TG201 lists the item that you need to implement quality control for, the methodology and how you would do that, and what I specifically like as a busy clinical physicist, they actually give you the time that it takes to do these tests. This is absolutely great for work planning, and I wish we would implement that in more task groups. That's the goal. So now that our data is crossing between the different elements of our IT infrastructure correctly, we have lots of data available, and now we can jump into big data and figure out what that data trends that we're measuring, either by log file QA or with the IT process, can actually tell us. Statistical process control is one of my favorite topics for QA. So let's say you have a treat, no treat decision based on TG218 criteria, and you get a bunch of IMRT measurements over the year. Now you can file these processes and give them two process attributes. You can have a very stable process where you just have the usual, random errors that you get when you do any measurement. But you could also have an unstable process that has not only random, but also systematic errors. An example is you have a brand new Linux, the output is still a little bit settling as the machine, gets into its working state, and you can have these sudden shifts of output at times. Here's a just schematic plot how that would look like. You have a random process here that fluctuates until around a mean value. And when a systematic error is introduced, you just could suddenly get a process change. So there's only a couple of process control parameters that you actually need. You need a basic initial data set where you can calculate the mean and standard deviation. And then you can define the process ability as a function of that mean, p bar, times the standard deviation, and then you can set a parameter t with an empirical value. And t drives the percentage of cases that will flag as having a systematic error. So you don't want that too small, obviously, because you have these tails of the random error distribution that could flag as systematic. And you don't want it too loose, because then you never ever pick up a systematic error. And so from that, you can actually derive 4 process states in this matrix. You can be within specification or outside the specification. You can be in control or out of control. We want to be in the green box. But what's really interesting to us as medical physicists is this yellow box here of a control process that is still within specification. All your QAs still pass, but it's really outside of the control. So you have this step suddenly of the distribution that indicates that you have a systematic error that has been introduced in the system. So statistical process control can actually help us pick up these systematic deviations before they become major clinical problems. We can close the quality gap using that system. Here's one example of how that would look like. Prostate, IMRT QA, fairly standardized, simple plans. You have the clinical specifications plus minus 5% would get your QA to pass. Based on your initial data set, you know that you have actually a standard deviation that is looks like plus minus 2 and some odd percent here around a mean value that's slightly different from 0. And your control limits, the t parameter that you wanted to dial in. For this, you can set it actually fairly tight because you have fairly small random errors, and so it doesn't flag very often. This plot looks quite different for head and neck plants that typically have a lot of modulation. And in 2008, when this paper was published, our machines were much less capable than nowadays to deliver these complex plants. So what you can see is you still have a mean around 0. Your clinical specifications is plus minus 5%, but based on the data set that you use to set your control limits and your standard deviation, you can actually see that the standard deviation is on the order of slightly larger actually than the clinical specification. And your control limits need to be set even a little bit wider, because otherwise you'll get frequent flags of systematic errors that are actually just the tail ends of the random distribution. So far, I've talked about computational methods that can be applied to the quantifiable components of the IMRT chain, but there are non-quantifiable components as well. So AAPM Task Group 100 was the first task group that really pointed to the gaps in the pre-treatment QA measurements or computational QA in several components. And here on the right, you can see the IMRT process tree that is happening, simplified actually, that you can find in TG100. So first of all, when you do measurement QA and something fails, that means you caught an error after it was introduced into the system. That is not very efficient. IMRT is also way more than just a technical component. There is this whole process, again, right slide, very complex, and there's also human factors that you have to consider. And TG100 really pointed out that these prescriptive QA that we had before was really a somewhat ineffective use of resources, because it's not driving us toward focusing on high risk priority numbers or high severity failure mode. So let's do a quick recap of FMEA methodology. You get a multidisciplinary team together that determines all possible failure modes in a process in the absence of any QA or QC. So it's a brainstorming forward search of failure modes. Then you assign each of these failure modes probability of occurrence, severity, and a detectability. And you multiply these three numbers to get a risk priority number. What you then do is you sort these risk priority numbers, and you focus your QC and QA efforts on the highest risk priority numbers, and in our specific field also on the high severity events, those catastrophic errors. So how are we using this systematic FMEA guidance within AAPM? Every newly formed clinically oriented task group now has to have a section on FMEA on their specific topic. There is a committee on TG100 implementation that drives a lot of the educational opportunities, specifically training classes at AAPM and chapter meetings on how to conduct an FMEA. We also have now a very solid library of peer-reviewed publications and opportunities to share data on FMEAs. Well, FMEA has limitations, as good as it is. First of all, it's a time and staff intensive process. The clinic teams I've worked with did FMEA 3 times in the last 12 years, because it's just really difficult in a time where hospitals are optimizing their staff, means minimizing any extra time they may have. And we also had questions about actually how to quantify the outcome. The other obstacles we ran into was constraints on implementation. So there's regulatory requirements that we have to fulfill. Accrediting organizations have requirements, and there's also hospital procedures. And fun side note, we actually dropped a specific equipment test from monthly to quarterly in my institution, because our FMA showed that this was a low risk thing to do and fairly high value in terms of time spent on that. And we get dinged at every accreditation for that, even though we show them the FMEA study. So there's still clearly some implementation things that have to be worked out. Also, more generally, FMEA methodology starts hitting snags when there are processes with lots of complex feedback loops and also when there's imperfect system design. And this brings me to something that I've also just recently learned, and that is system theoretic process analysis. This comes out from engineering. Actually, Nancy Leveson, who is an engineer at MIT and got involved in radiation oncology safety with the original Therac accidents in the mid-80s, is one of the drivers of this. And STPA is used for very complex systems that we have nowadays. It is a backward search starting from hazardous states that we want to avoid. And unlike the fault tree analysis, STPA can actually include design flaws of the system. And the core of an STPA analysis is that you draw out a control loop. So you have a controller that has a process model and the control algorithms, and the controller acts on the controlled process and you get feedback from the controlled process. And so you have a loop here, and then you also have some environmental inputs. I won't go too deep in here, but this is an example how this process loop looks for a treatment design controller for a typical radiation oncology system, where you have multiple interlocked process loops, multiple controllers with controlling actions and feedback loops. So how do you start with an STPA? You first create a list of high-level accidents. For radiation oncology, is typically injury to patient or staff or equipment damage. Then you create a list of system hazards. So these hazards are states of the system that would lead to the accident you defined in item 1. And you limit yourself to 10 to 12 hazards at the very beginning, and you can always refine that later in this iterative process. So very different from FMEA, where you typically start with literally hundreds of failure modes. After you have the accidents and hazards, you create a safety control structure that I showed you in the previous slide. Once you have that structure in place, you identify unsafe control actions. And once you have that list of unsafe control actions, you do a root cause analysis and identify causes for unsafe control action. Here is an example from Dr. Pawlicki's paper of an unsafe control action for the medical physicist as a controller. And for each control action, you have, in general, 4 different types of things that can go wrong. The control action is not given. The control action is given incorrectly. The control action is given at the wrong time or wrong order. Or the control action is stopped too soon or applied too long. So here for the fusion of MR and pre-plan to cone beam CT, if it's the wrong time, images are fused before the final or most recent cone beam CT is acquired. You can actually link back what hazard of the hazards you've identified this could cause. So there's a link back to the hazard list. Once you have this the situation here, the scenario, you can think about how to redesign the process and implement quality control so the system never reaches this specific state. So in summary, STPA is designed for complex processes with multiple feedback loops, is a very systematic way in catching design flaws in a process using a backward searching methodology. From the papers I've read, it seems that it's a very complementary process to the FMEA that can give you additional information based on the different way of thinking. The investigation for its use in radiation oncology is just starting. I see the first papers popping up, but there will be probably much more about this fairly soon. There are other methods, of course, systematics and computational methods for IMRT-QA. AI has made an entry recently for monitoring error propagation in IMRT process, to predict pass rates, and to analyze the types of errors you find. And I even found one paper on radiomics-based error classification. So in summary, the safest solution in our optimization problem of IMRT safety in the year 2005 is definitely not the safest solution in the year 2022. The Pareto surface or the Pareto border has changed. Our equipment is much more robust. Software and data transfer has changed a lot. Safety science itself has developed further, And medical physics as a profession has changed. We are educating ourselves a lot more about these topics, and we are learning, like in this workshop. And all these things, I believe, create an obligation for us to change clinical practice as the years pass. I do want to acknowledge that there are barriers to change. Change is scary and risky, and the AAPM Leadership Academy has a lot of lectures and helpful information on how to navigate that process. There are regulatory and legal concerns about changing process. And there's, of course, with the reimbursement that happens in the United States, are also financial concerns. And I believe Jerry White has a lecture on that in this workshop. But I do believe that as time goes on, that we as medical physicists, as our profession, that we can find the correct balance between optimizing the safety, shrinking that sigma, narrowing the quality gap, minimizing the number of patients that come to harm, and that we can find the right balance. So while at the same time being aware of that, while we have to talk about statistics of large numbers, every single patient trusts us to do the right thing. And just keep that in mind whenever we make decisions to change a process. Thank you for your attention.